This lesson deals with a filtered full-wave rectifier circuit. You can find these notes in the ECE302 ebook in Chapter 2, starting on page 47. In the last video, we looked at a bridge rectifier with a resistive load and found that the voltage across here had an average value that wasn't zero, but it went zero several times per second. And so if we make this into a power supply, that won't work out well because we're actually shutting the voltage off so many times per second. If you recall in ECE201, we used a capacitor to hold the voltage at a particular node. Let's put a capacitor across here. I'm going to use a 60 Hertz sine wave of 20 volts coming in. I'm going to use our default values in our textbook for I sub S and eta. And we got a description here of our schematic. I'm going to pick the capacitor to be 47 microfarads with a 1K resistor. That's going to give me a time constant, like we talked about in ECE201, and that's 47 milliseconds. The period here is 1 over 60, but we're going to take a look at the fact that we're doing 2 of these per cycle, and so the frequency is actually 1 over twice that number, 1 over 120. That's 8.33 milliseconds. This time constant is much, much greater than half the period. That'll be important as we go through this particular section. I also ran the simulation without the capacitor so you can see the effect of it. I want to plot 3 cycles. 3 times 1 over 60 is 50 milliseconds. I want to divide that by 2,000 instead of 200, so I'm going to get a lot more data points. Start a simulation printing at 0, and then we'll pick the sealing step the same as the print step. And here's my output. I ran 2 simulations, and I wanted to show you what the effect was without the capacitor, and that's what our bridge rectifier is doing. And then when I ran the capacitor, you can see the effect of it. It followed here, the waveform, and then as this went back down again, this began to just droop slowly, and eventually this catches up to it, and then it goes back up again and it repeats itself. Peak voltage here is 18.305 volts, and my peak was 20. So if we take that difference and divide it by 2, you get about 0.8475, and so that's roughly the drop across the diode. The value over here drops from 18.305 to 15.889, and that difference of these two is called the ripple voltage, because it looks like ripples on a pond if you were to throw a stone at it. It's generally given in peak to peak. In this particular case, the difference between these 2 points is about 2.416 volts peak to peak. You have 2 simulations together and you want to look at just one of the simulations. You can use the symbol @1 or @2. My first simulation was with the capacitor. So here is the current in diode 2. And I did it with a dotted line and a regular line. The dotted line is the current in ID3. And you can see it's kind of sequenced between the two. And you can see here that these spikes are associated with part of the curve. And this part over here where the curve goes up, I get a spike of current in diode 3, and actually diode 1. And over here, when I get this spike, this is in diodes 2 and 4. And likewise over here, this is for diodes 2 and 4. I separated out that last graph. Here's the current in diodes 2 and 4, and here's the current in diode 3. So you can see what's happening here. We're getting a surge, another surge, and then repeating that surge again. And then over here for diodes 1 and 3, we only see that surge like this, but we don't see this one. So we'll try to figure out why that's happening. I also plotted the current in the capacitor, and you can see that the current here also shot up, and the value here is 351.455 milliamps, and the peak for the current in the diode was almost the same number. It's a little bit bigger, it's 352.031 milliamps. And then here's the current in the resistor, which is also the voltage across the resistor divided by the resistance. And you can see that it's following the same shape as the ripple voltage. Note on the capacitor that the current is positive here, and so on here, but actually goes negative at this point, and current comes out of the capacitor. So here it's going into the capacitor, here it's coming out of it. And we're seeing roughly a fairly constant current, about 17 milliamps, and then we're seeing these surges here in the capacitor, about 150 milliamps. Plotted again, node voltage 2 of the first simulation, this one that has the capacitor in it, and the peak value here is V sub S maximum minus 2 diode drops. And then we drop down by a value of the ripple voltage. So we're just going to subtract that off of that. So that's the value over here. Label this time T1, T2, T3, and T4. I want to talk about what's happening during these time intervals. Between 0 and T1, the input voltage isn't big enough to turn on the diodes. All 4 diodes are actually off. Time T1, our input's going up, and we're seeing that diodes 2 and 4 are on, and 1 and 3 are off. The output voltage is also the capacitor voltage, and that's going to be equal to, if we go around the loop, we have this voltage back through here. We have V sub S minus 2 diode drops, just like we did in the bridge rectifier. And the current in the capacitor is the capacitance times the derivative of the voltage across it, which is also the derivative of V out. V out is a sine wave of 20 times the sine of 2 pi ft. F is 60 hertz here, but we leave it symbolic. And I got 2 diodraps to subtract off. Take the derivative to predict the current in the capacitor. We take the derivative of this. The derivative of a constant is 0. If we have a scalar in front, that's still here, so that's 20. The derivative of sine is cosine of the same argument, and then we take the derivative of what's inside the bracket with respect to t, and that's 2 pi f. So we could approximate t1 as being close to 0. In other words, this is about 1. I get 20 times 2 pi f times 1 would be the derivative. If you multiply that by the capacitance, you'd roughly predict the surge current. That turns out to be 354 milliamps, and in the simulation we found it was 351.5. So some of our approximations here are accounting for that little bit of a difference. We're getting a one-time surge of current. We call this a non-repetitive surge in a datasheet. It's related to the slope. The fact that when we start out the sine wave, the slope is maximum, and that's going to multiply the capacitance. We're going to get a surge of current. Can the diode withstand that? That's one of the numbers in the datasheet when we pick a diode. What happens at the time t2? At the time t2, our input voltage has a change in slope. It was positive here, and thereby current went into the capacitor. And now the slope is equal to 0. When the slope is 0, the capacitor current is 0, and the current in the resistive load is the same as the diode current. And the current in the resistive load we measured as 18.305 milliamps. That was also through a 1K resistor, and that would give me a voltage of 18.305 volts. The charge that's stored on a capacitor is equal to the capacitance times the voltage across it from ECE302m. It's going to be 47 microfarads times 18.305. We've deposited 860.3 microcoulombs of charge on the capacitor at that instant in time. The capacitor is a storage device, and we can take that charge back. What happens next? At t equals t2 plus, the slope of our input voltage, minus 2 diodraps, has gone from positive to 0 to now being negative. And when the slope goes negative, that's also the voltage across the capacitor, current has to come out of the capacitor. Can that current go this way? Can the current go this way? The answer is no. It can only go in the resistive load. The capacitor is holding the voltage from changing rapidly, as we can see, and the input is starting to decrease. Here we have our sine wave coming back down again. And a little bit beyond T2, the voltage is small enough compared to the voltage here now so that all 4 diodes are off. Now what does our capacitor see? Well, it sees a resistive load. What's going to happen? Between times T2 and T3, we have a capacitor and a resistor in parallel. If you look in ECE301 in our ebook, in Chapter 7 on pages 4 to 8, we talked about RC circuits, charging and discharging. One of the formulas we can derive is that the voltage across the capacitor at the initial condition, which was V sub Sm minus 2 diodraps, in this case 18.305, and that's multiplied by an exponential that starts out at, in this case, T2, and then as T increases compared to T2, we begin to exponentially decay, based upon the time constant, which is R sub L times C sub L. In these notes in ECE301, we showed that it takes about 5 time constants for this exponential to decay to almost 0. The interval T3 minus T2 is a little bit less than half the period, which is 8.33 milliseconds. And that's much less than the time constant R sub L C sub L of 47 milliseconds. What we're going to get is not an exponential decay to 0, but just simply a long drawn-out exponential, which will look more like a straight line. That's what we saw in the previous graphs. So in this interval T2 to T3, we have that the output voltage is V sub S maximum minus 2 diodraps times e to the minus t minus t2 over tau. That's describing this curve right here. Now when t is equal to t3, we also know the value of the voltage. It's equal to V sub S maximum minus 2 diodraps minus what we call the ripple. We're going to solve for the ripple voltage shortly. That has to also equal this equation when t is equal to t3. And now we can solve those two equations for the ripple voltage. We'll take these two equations right here. Put this on the other side of the equation, and then bring this on this side of the equation. So we get V sub S maximum minus 2 diodraps times 1, and then times a minus e to the minus t3 minus t2 over tau. T3 minus t2, that's a little bit shorter than half the period. Half the period is t4 minus t2. Plug that in, it's an approximation. I have e to the minus t over 2 divided by tau. I've got an exponential where this term here is less than 1. Our value of tau is much larger than half the period. We had an approximation back earlier in the chapter. on page 15. E to the x is 1 plus x if the magnitude of x is less than 1. You can represent this term right here as 1 plus x, but x is equal to minus t over 2 tau. The two 1's cancel, and I just get t over 2 tau. The ripple voltage is approximately equal to the peak of E sub s maximum minus 2 diodrops divided by 2 tau, which is 2 times R sub L C sub L, and the period is 1 over the frequency. I have a formula for the ripple in terms of the capacitive load, the resistive load, and the frequency. This is true provided that my time constant is much, much greater than half the period. You can also calculate V out average, which we designate as capital V sub capital 0, and that's going to be equal to roughly the middle of that rippling voltage, which is the peak of V sub s maximum minus 2 diodrops and then minus half the ripple. If we approximate VD on as 0.7, we could calculate the ripple voltage peak to peak. It would be 20 volts minus 2 times 0.7 divided by 1 over 2 pi f, 60 hertz, R sub L, 1K, and C sub L, 47 microfarads. That's equal to 3.298 volts peak to peak. On our simulation, if we take the difference between the max and the min on that ripple graph, it's 2.416 volts peak to peak. Now the reason we're off is about 26%, is that we made an approximation that T3 minus T2 was equal to half the period, but it's actually a little bit smaller than that. In fact, it's about a third less. That's where we're getting roughly that 26% error. But the good news is that when we calculate this, the actual circuit's going to be better. This formula is just an estimate. But what it does show is that if you increase the frequency, you lower the ripple. If you increase the capacitance, you lower the ripple. But if you decrease the resistance, you increase the ripple. You have a bigger load to drive. In other words, you have more power you want out, going to make the ripple go up. And we can compensate for that by putting a bigger capacitor in. We can likewise calculate the average output voltage. It's going to be 20 volts minus our 2 diodrops. Again, just doing generic 0.7. And then half the ripple, what we can calculate. So again, all this is our approximate formulas. We get about 16.951. If you take the max plus the min divided by 2, you get 17.097. That's less than a 1% error. And the reason why it's small is because this number here dominates the numbers that are here. At T3, our output voltage has dropped to 15.889 volts. And the charge stored in the capacitor then is just simply the product of the capacitance times the voltage, and that's now 746.8 microcoulombs. We had started out with 860.3 microcoulombs, and now we've dropped to 746.8. We've lost 114.5 microcoulombs of charge. Time t equals T3, the input is starting to catch up to the output. Output was dropping, and then our input's coming back again and going back up, and at t equals T3, we begin to see now the diodes conducting. In this case, 1 and 3 will conduct. And we're going to replace the charge that we lost. Between T3 and T4 now, we have our diodes conducting, in this case, diodes 1 and 3. And most of the current that flows in these diodes goes into the capacitor C sub L, if you look at our initial simulation. And what's happening is the capacitor is resupplying that charge that was lost. Here we charged up the capacitor, here we discharged the capacitor, and now we're going to replace that charge, discharge it, replace it, and so on. The interval here, T4 minus T3, is pretty short. It's actually about 1.5 milliseconds, compared to T3 minus T2, which is 6.82 milliseconds. So we have much less time to replace the charge than when we supplied it. And current in general is the change in charge per change in time. In a short interval of time, we're going to see a surge in current. We get a handle on some of the numbers that are there. Let's try this. Go back to our schematic. The current in diode 2 plus the current in diode 3 is equal to the capacitor current and the resistive current at every instant in time. Some of these currents are passing through 0 and so on. What we could do is take a look at the idea that the average current in a capacitor is 0. So if I find the average value of both sides of this equation, I can find a new form of Kirchhoff's current law. This is the fact that the average current that enters a node equals the average current that leaves. Let me show you the derivation for that. We'll take this equation and then we'll integrate both sides, dt, and then divide by the period. And this is the definition of the diode current 2 on the average. This is the diode current 3 on the average. This is the capacitor current on the average, and this is the load current on the average. But the average current in a capacitor is 0. The average current in the two diodes has to equal the average current in the resistive load. And we can quickly calculate that. The average current in a resistive load is the average voltage across it, which we have a formula for now, divided by R sub L. Let's call the average current in the diode capital I sub capital D. That was the notation we were using for average values. I've got two of these, and that's got to equal this V0 over R sub L. So I can now solve for the average current in the diode as 1 over 2 multiplied by V0 divided by R sub L. It's half the current in the load. This particular number is also a datasheet rating. This is the repetitive surge current on the average. So we need to make sure we pick a diode that can withstand this particular number. These are some of the properties of a filtered full-wave rectifier circuit.